Okay, I think we're live. So welcome to this London Bitcoin Devs online. We'll be joined by Kalle Rosenbaum, the author of Grokking Bitcoin. In terms of London Bitcoin Devs, you can follow us on Twitter at LDN Bitcoin Devs. We have a YouTube channel where we have a bunch of presentations from the last 2 years with people like John Newbury and Matt Corello and Andrew Polstra, so check those videos out. We're also looking for future speakers. So if you're a Bitcoin developer or a Lightning developer, get in touch and we'll see what we can do in terms of either doing a Socratic seminar or a presentation, or maybe both. So we did have a Socratic seminar last week. The transcript is posted on the meetup page and on our Twitter page. So that was a really interesting discussion. Maybe during the Q&A we can continue with some of those discussion threads. In terms of Kalle's presentation, you'll be able to ask questions during pauses in the presentation. Apart from the pauses, everyone will be muted, and then there'll be a Q&A afterwards. I think Kalle is going to be focusing on chapter 10, which is SegWit, but in the Q&A, feel free to ask about any of the content in Grokking Bitcoin. In terms of asking questions, if you're not on the live call, you can ask questions on Twitter, comments in the YouTube video, or on IRC. We have a channel which is #2# LDN Bitcoin Devs, or £2 LDN Bitcoin Devs. So let's get going. We are live streaming on YouTube, so anybody who's on the call, please behave yourself. Okay, Kalle, take it away.
Okay. Thank you very much. I hope you all can hear me well. Yeah, I am going to talk about my book, Grokking Bitcoin. And to do that, I will do that in 2 parts. The first part will be a meta part, where I talk about a little bit about myself and also about the book and what you can expect from it. And the other part will be a deep dive into one of the chapters, which is chapter 10 on segregated witness, or SegWit. So first, I'm going to talk about myself a little bit. So I'm Kalle Rosenbaum. I like to lay on a bed of Easter lilies reading a good book. And if you want to reach out to me, you can do that on Twitter at Kalle Rosenbaum. And you have my PGP fingerprint there as well. I think that's all about me. So let's talk about the book itself now. Grokking Bitcoin is a look under the hood of Bitcoin. It explains how Bitcoin works technically and how it achieves censorship resistance, which is a very important property of Bitcoin. And who is this book for then? Well, it's for technical people, technically interested people, people that need to understand Bitcoin on a deeper level in order to, well, because they need it for their business needs, or they need to gain better trust in the system because they want to probably maybe invest in Bitcoin. And to do that, they need to gain more trust in the system. So this is one way of gaining that trust. And maybe you're just curious. So these guys, these tech people, they don't have to be developers, absolutely not. So there is no code in this book at all. But it's also great for devs, because I teach Bitcoin as is. There are very few analogies. It's just plain Bitcoin. And I describe the data structures as they are, and I describe the algorithms as they are. I just don't do it with code. I do it with concrete examples and lots of illustrations instead. So this is a book that I would have loved to read when I started out, and I'm a long-time developer. So so I would have loved to start with this to get a very good understanding of the concept of Bitcoin before digging deeper into code. And this book started out in 2016 when the publisher Manning Publications contacted me and asked if I wanted to write a book about blockchain. And I said, well, it was peak blockchain back then. But I answered back and said, well, no, but I'd like to write a book about Bitcoin, please. So we started negotiating terms there. And one of the requirements I had for this book was that it should be open source. And they agreed to that after a while. So it's now open source on GitHub under Creative Commons license. But you can't read the book on GitHub because you won't see the images or anything there. You need to build a book before reading it. But to make it easier for you, I have made a build myself that I put up on my website. So you can reach the build at rosenbaum.se/book. So please head over there and have a look if you want. It's a great way to try before buy, by the way. And if you want to buy the book, it's available on Amazon or any other major bookstore, and as well as on Manning's webpage, manning.com. I also want to brag about the foreword that's written by the excellent David Harding. David Harding is a technical writer, writes a lot of documentation for Bitcoin and also contributes a lot to bitcoincore.org. And he's also a major contributor to the Optech newsletter that's sent out every week. I recommend everyone to read that newsletter. It's great from a technical perspective. The book is also translated into a few languages. It's the translations for German and Japanese are finished. The German translation is done by the great Volker Herminghaus, who did this in a very short time, and he did it open source. So this translation is actually part of the source tree on GitHub. And there's also a commercial Japanese version now, came out in March. And there are several other languages in the making. Finnish, but they're still trying to finish it. Spanish, Portuguese, Russian, and Polish, but that one needs a little bit more Polish. So let's talk about the structure of this book. The book contains 11 chapters and a few appendices. The first chapter, chapter 1, is your typical overview of Bitcoin. It describes why Bitcoin matters, why censorship resistance matters, and how Bitcoin operates on a very high level. And chapter 2 introduces two very important concepts in Bitcoin, that is cryptographic hash functions and digital signatures. And it also sets the stage for the rest of this book. So chapter 2 sets the stage for the rest of this book by creating a very, very simple payment system or money system that we call cookie tokens. You can use these cookie tokens to buy cookies, for example, at the cafe. And the cookie tokens are being tracked in a spreadsheet, an online spreadsheet that only one person has write access to. Everybody can read this spreadsheet, but only one person named Lisa has write access to this spreadsheet. So when John wants to buy a cookie from the cafe, he asks Lisa to move 10 cookie tokens from him to the cafe. And Lisa does that by updating adding a row to this spreadsheet. Of course, this spreadsheet has a lot of problems. You can't use this as global censorship money. So we will, chapter by chapter, add Bitcoin tech to this spreadsheet. And in chapter 8, we will end up with Bitcoin. So chapter 3 changes the names that you saw in the spreadsheet with public key hashes to make this spreadsheet more private. Chapter 4 adds the concept of a wallet that manages the keys for you and also standardizes a message that you send to Lisa. But Lisa still updates the spreadsheet just as she did before. One problem here is that Lisa can easily steal money. She can just change anything in this spreadsheet to increase the amounts for her, for example. And that's not very good. So in chapter 5, we introduce the concept of a transaction. A transaction, and we changed the spreadsheet into a list of transactions and introduce the concept of the transaction. So now everybody can read this list of transactions. And the transactions, as we know, contains the signatures. So if Lisa can no longer steal money by changing data in the transactions, but she can still delete transactions from this list without no one being able to prove that she did. So in chapter 6, we introduce the blockchain, or rather a blockchain. This is not the blockchain. So in order to stop Lisa from deleting transactions, Lisa now needs to collect transactions into blocks that she signs with her private key and publish those blocks to a shared folder. I'll get back to this shared folder in a moment. But this way, since the blocks are signed by Lisa's private key, she can no longer remove transactions from blocks without being proven a fraud. But this still has problems because Lisa can still prevent transactions from entering the blockchain in the first place. She can still select which transactions to add to the blocks. So she's still a central point of censorship here. So in chapter 7, we fix that by introducing proof of work. With proof of work, anyone can become a Lisa. Anyone can become a miner and create blocks and put them on the shared folder. And this means that if Lisa won't process my transaction, I'm sure somebody else will. So we are heading closer to a censorship-resistant system here. But there's still a problem. You remember the shared folder, right? So it's time to get rid of this shared folder because there's a shared folder administrator who has ultimate access or power over what can enter the shared folder. So the shared folder administrator can censor blocks. And to stop that from happening, we create this peer-to-peer network where block producers now publish their blocks on a peer-to-peer network. So blocks, so a block producer will probably publish it to multiple peers who will then verify them and relay them to their peers and so forth until everybody has the blocks. And this is pretty much Bitcoin we have created here. So from this point forward, we discuss only Bitcoin. We leave the cookie token system from now on. And this is chapter 8, and the last part of chapter 8 discusses how you install or how you start your own full node, and it also includes a tutorial on how to do that on the Linux command line. That's as close to source code we get in this book, I guess. And there are 3 more chapters, 9, 10, and 11. Chapter 9 is about transactions, more about transactions. We pick up where chapter 5 left off. We talk about replaced by fee, sequence numbers, check block time verify, and stuff like that. And chapter 10 is about SegWit that we'll dig deeper into in the other part of this talk. And chapter 11 is about Bitcoin upgrades. It talks about soft forks, hard forks, deployment mechanisms, and how certain features were deployed in Bitcoin. So I think that concludes the first part of this talk, and I think this is a good time to take questions if there are any.
I've unmuted everyone. So does anyone have any questions? Some of you guys were at the Socratic last week, so feel free to bring up some of the topics we discussed at Socratic. Any questions? No? So one from me then, Kalle. So yeah. How much did you dog food this book? So I think most of the people on this call have probably been into Bitcoin for a while, but like especially with the intro stuff, how many people did you get to go through the basics of Bitcoin, and what was their feedback, and did it require any iteration?
Yeah, actually Manning was very valuable there because they provided me with a lot of reviewers. And I wanted reviewers that had little to no experience in Bitcoin before, but I wanted technical people, but not necessarily Bitcoiners, or preferably non-Bitcoiners. And they provided extremely valuable information back to me. And we did, well, quite a bit of revision there. And I also had certain chapters out to different experts. I had a cryptographer looking at my cryptography explanations, and people looking at chapter 1 to make it, accurate enough. So yeah, quite a bit of revision there.
So it sounded like you did a lot of work to ensure the accuracy, but did you get some beginners to go through the content and see how useful it was to them or accessible it was to new people?
Yeah, so we had like 13 reviewers from Manning, or Manning have a pool of reviewers.
So the Manning guys were all beginners.
Yeah.
Coming into Bitcoin.
Right.
Okay, makes sense. Any other questions? I think everyone's unmuted, so.
Just a quick one from me.
Mm-hmm.
Yeah, it's I haven't got through the whole book yet, but it's brilliant. Just actually, how long was the process for you from start to finish to pull this together?
Yeah, good question. It took ages, 2.5 years, probably. So Manning contacted me in autumn of 2016, and it was published about a year ago now. So 2016 autumn, yeah, 2.5 years. So it was a pretty tough process. The writing phase was like 1.5 year or so, and then the production phase was pretty extensive, with reviews and with typesetting and copy editing. That process was a nightmare actually. But the end result was great, and I'm actually quite glad it took that long, because it wouldn't be this good otherwise. So we also had we had problems with the first illustrator. I did the drafts for the illustrations, and then a professional illustrator redid them for me. But the first illustrator wasn't great, so we lost like several months there trying to get him on board. But eventually we actually changed to another illustrator. But we lost a few months there. That's sad, but the end result is great. So I'm happy we did that.
And do you intend to sort of like see this as a work in progress? And obviously as Bitcoin evolves, and do you intend to add to it? And
I'm sorry, I couldn't hear you.
Or do you intend to sort of keep this as a work in progress? Can you hear me now?
Yeah, I can. Yeah.
and you know, sort of add to it, obviously with Bitcoin evolving. Yeah, do you intend to do that?
Actually, not really. Maybe I will do a second edition of this book. It's not in the making right now. We'll see what happens. But right now, I'm pretty pleased with not writing. So, so we'll see what happens in the near future here. But I can't say anything about that now.
Cool, thank you.
And what point did you get into Bitcoin, Kalle? I saw your name was referred to in a Scaling Bitcoin presentation back in 2015. So you're into Bitcoin pretty early.
Yeah, yeah. I talked about something called IBLT, invertible Bloom lookup tables, back then, and I presented some work that I did together with Rusty Russell. So we presented together there at Scaling Bitcoin. That was very, very fun and very interesting. So it had to do with improving the efficiency of block propagation with a certain data structure that we call IBLT. So that was fun.
Very cool. Okay, we'll let you move on to the next section.
Okay, let's move on then.
I'll mute everyone.
Yeah, I'll take my earphones off then. Okay, so let's see. Yeah, so the second part of this talk is about SegWit, or segregated witness. That's covered in chapter 10 of the book. And I will do that by presenting a problem and the solution to that problem. There are several problems that SegWit solves, but I will focus on just one of those problems in this talk. Please refer to the book for the rest of the problems. Yeah, so the problem I want to talk about in legacy Bitcoin is transaction malleability. You probably heard the term several times. To malleate something means to deform. So you can malleate a sheet of metal, for example, with a hammer. And that's about the same as what happens in Bitcoin, in transaction malleability. So suppose you have a wallet and you send out a transaction, TX2 in this example. You send it to Tom's node and Tom verifies it and sends it to his peers. But there's a problem here. She's node is a malicious node. She does everything she can to make your life miserable. So what she does is she takes this transaction 2 and makes some subtle changes to this transaction without invalidating the transaction. She can make some small changes to the transaction, and then she publishes or forwards the maleated transaction, the changed transaction to her peers. So now we have two transactions floating around the network. We have TX2 and TX2M, which is the maleated version. Now, these two transactions are extremely similar. They spend the exact same coins, and they send the coins to the exact same addresses with the exact same amounts. And that might not seem like a problem, you might think, but there are problems with this. And I will come back to why this is a problem soon. But right now I will focus on what she has done to this transaction, or what she could do with this transaction. And to do that, we will look closer at transaction 2. In this example, the transaction looks like this. I usually draw transactions like a rectangle like this with a vertical bar in it. To the left of the vertical bar are the inputs, and to the right of the vertical bar are the outputs. And this particular transaction has only one input and one output. So what can she do now to maleate this transaction without invalidating it? She can. The only known way to do that is to modify stuff that's in the signature scripts. The signature script is the stuff here that you see within the bracket. In this example, the signature script consists of a signature and a public key. And if we look closer, we see that the signature is, in a way, encoded by a, let's call it a signature container. So it's encoded in a certain way. So we have the signature container containing a signature, and you have a public key. And I'm going to present you 3 different ways to maleate this transaction. And there are others too, but I'll show you these 3 classes. The first thing she can do is to alternate the encoding of the signature, or the container format. There are a few different ways you can encode the signature without that are all valid. So you don't change the signature itself, just the encoding of the signature in the signature script. Another way to maleate the transaction is to apply some cryptographic tricks to the signature itself. So there is at least one such known way to do that you can apply to the signature itself without invalidating the signature. And the third thing I want to mention is that you can add operations to the signature script that together does nothing. In this example, we add a op-dupe followed by a op-drop, which means duplicate the top item on the stack and then drop it again. So this is together a no-op, so it doesn't change anything in the script, but it changes the transaction. Okay, so now we have the possibility to maleate the transaction. And why is that a problem then? The transaction still does the same thing. It spends the same coins and it sends the coins to the same outputs. So why is it a problem? To understand that, we need to understand the concept of transaction IDs. This is actually from chapter 5, but I reiterate it here. Transaction ID is calculated from the whole transaction, including the signature script. So if you maleate anything, if you change anything here in this signature script, you will also change the transaction ID, because the transaction ID is calculated by hashing the whole transaction, including the signature script. So changing the transaction will cause a change in the transaction ID. And why is that a problem? That might oftentimes not be a problem. For simple payments, if another transaction than the intended one gets confirmed, it's usually not a problem for simple payments. It might cause a little confusion for the wallet, but you still have your money safe. But it's not always the case that you use. Payments aren't always simple. Oftentimes you need to create chains of transactions before publishing any of the transactions. So, for example, when you set up a Lightning Network channel, for example, you need to first create a funding transaction. Let's call this transaction 2 here, a funding transaction. You create that transaction, but you don't publish it yet. And then you create transaction 3 here, which spends the funding transaction and sends the money back to you somehow in case of a dispute. So when you have created transaction 3 safely, then you dare to publish transaction 2. And as you see here, I draw hashes like this. It's a little pile of paper. This transaction uses the transaction ID of transaction 2 to refer to transaction 2. So transaction 3 references transaction 2 via its transaction ID. So suppose now that you have created those two transactions transactions, and you then decide to publish transaction 2. So you publish transaction 2, and this happens. She maleates your transaction. So there's 2 transactions floating around the network, and you end up with this unfortunate situation. The maleated version of the transaction is the one that gets confirmed in the blockchain. And as we know, the maleated transaction spends the exact same coins as the original transaction, which means that transaction 2 now is forever invalid because it spends coins that are already spent by another transaction in the blockchain. Okay, so transaction 2 is now invalid forever. And that means that transaction 3 is also invalid forever, which means that this whole contract is totally broken because of transaction malleability. Okay, so let's recall why this is a problem now, or why this occurs. Sorry. This occurs because changes in the signature scripts causes the transaction ID to change. Yeah, so this is the problem part of this part. So before I go into the solution of this, maybe we should take questions if there are any.
Okay, I've unmuted everyone. There are some questions on the YouTube, but I think they're probably best questions for at the end. Okay. They're not specific to the content thus far. So the obvious example. Anyone have questions?
Yeah,
yes, Sebastian.
Short question. Yeah. So I remember first hearing about transaction malleability back in 2014 when there was quite a few funds missing on Mt. Gox. So you were already around back then, Kalle. Can you explain? And Mark Capellis at that time claimed that transaction malleability was to be blamed for the loss of funds. Do you have any comment on that? Is that a plausible explanation, or can you give a short explanation what happened there?
I rather not. Maybe it's plausible. I actually don't know.
Okay.
I'm sorry, I can't comment on it. Maybe it's plausible. I remember the discussion, but I don't remember any details at all.
Okay.
Sorry, I didn't hear the question. What was the question?
Sorry?
What was the question? Can you repeat?
The question was if Kalle had an idea that the explanation that transaction malleability was to be blamed for the loss of funds on Mt. Gox that actually led to the bankruptcy of Mt. Gox back then, but probably also for legal reasons, it's a good idea not to comment on that. I was just wondering. So,
yeah, I have no idea on that question either.
Maybe some other listener will know.
I don't think so. Lockie, go for it.
Yeah, this is a different question. Okay, so in this example, we now have 2 invalid transactions, right? So does that mean the funds are now locked?
Yeah, they are. Transaction 2M now contains the funding output, but we don't. If me and my partner cooperates on reclaiming those funds, we are good. But if my counterparty won't cooperate with me, the funds will be lost.
Got it. Okay,
it's very important that that the events happen correctly. Yeah.
And this has occurred, a lot in the past, or?
Transaction malleability have occurred a lot in the past because it was very easy and cheap to set up a Rouge node that just malleates for the lols. I don't think it caused much economic damage, but it caused confusion, of course, and it caused a vivid discussion on transaction malleability and various ways on how to prevent it.
So it was just malicious attacks, really. There was no benefit other than damaging a Bitcoin. Is that right?
Well, I can't speak whether there were much economic damage. Maybe there were, I don't know. Can I get back a few slides here? I forgot to mention one thing. Sorry, I'm going backwards. One little detail that I wanted to say about. Yeah, here. These are the 3 ways to maleate a transaction, but I forgot to say that this first way to do it is actually fixed by now. It's fixed in BIP 66. So there's a new consensus rule that prohibits this, but the other 2 are still possible to do, but they are limited somewhat by policy rules in the nodes. So a node won't relay a transaction that does this, but the miner can still do this. So, but back in the days, you had no policy rules against this. So it's, yeah.
So obviously Lightning is one thing that really needed a solution to this transaction malleability. Any other constructions or any other projects that needed this problem to be solved?
I think most complex constructs will get, at least they will be easier to perform without transaction malleability. So most contracts will actually gain from it, either because they suddenly become possible or because they suddenly become more easy to do, less convoluted. Examples, yeah. Don't know, actually. Let me pass on that right now.
I have a question. Can you hear me?
Yes, I can hear you.
Okay, great. So if transaction 2M was included in a block, it was confirmed. Transaction number 3, referencing the transaction number 2, will not be confirmed in a block, right?
Right.
So it's on a blockchain level, it's not a problem. So if someone puts transaction number 3 in a block, the other nodes will check the block and will found that transaction number 3 don't fits in, because
exactly.
But do you know if the miner checks it after it's in a mempool? So they have transaction 3 and transaction 2.
I'm not sure what you're asking for here, but as you say, if someone tries to create a block with transaction 3 in it, that block will be rejected by other nodes.
Yeah.
Because transaction 3 spends coins that doesn't actually exist in the blockchain.
Yeah. So it's officially not possible that my funds got locked on a blockchain level, isn't it?
Yeah. Well, in this case, when transaction 2M is the one that gets confirmed, this funding, if we talk about Lightning now, this funding transaction.
Yeah, okay, yeah.
Well, we talk about Lightning as an example. This could be any type of contract, but.
Yeah, this is off-chain then, right? Yeah.
Yeah, okay, let's go back to transaction 2 and 3 here. When we created them, you create transaction 2 and transaction 3, and transaction 3 is like a dispute resolution transaction. In case you don't cooperate on how to spend transaction 2, you can always publish your dispute resolution transaction but this dispute resolution transaction depends on transaction 2 being confirmed in the first place.
Yeah. So it's mainly a problem, an off-chain problem, right?
Yeah. It's only a problem for this particular instance of the contract.
Yeah. Okay.
Yeah. So the blockchain is fine, and everybody else's contracts are fine, but this particular contract is broken because of transaction malleability.
Okay. So transaction number 3 will get relayed, but if it's in the same mempool from the miner, and the miner don't have transaction number 2 and has transaction number 2M, it will be rejected, right?
Yeah, but I think it will be rejected even earlier. It will be rejected by each node. That when you try to propagate this transaction through the network, the first node it encounters will see that transaction 3 spends coins from an invalid transaction, or it doesn't even have this transaction because it's invalid. The node has already received this block.
Okay. So,
and if
okay.
If it had this transaction in its mempool, it will just drop this transaction because it's now invalid.
Okay, I thought transaction X2 and X2M were simultaneously relayed through the node network.
It is. They are simultaneously, but so for a while they are both in the mempool. But once transaction 2M gets confirmed in a block, then every node will drop transaction 2 because it's it's invalid.
Okay, great. Okay, thank you.
Okay. What do you guys think? Should we move on, or any more questions?
I think we can move on.
Right.
So I mean, just basically as a summary, there's no problem if you just have the transaction go on chain, and you don't need any transactions linking to that transaction, right. Like future transactions to link to that transaction. But if you do, and you're building constructions and projects that rely on referring to that transaction ID, then transaction malleability is a real problem.
Yeah, it's a great summary. Thank you.
No worries. But unless there's any other questions, feel free to move on to the next section, Kalle.
Sure, thanks. Okay, so let's just pick up here. We said that transaction malleability was a problem because of what Michael just said, and that's because the transaction ID is calculated from the whole transaction, including the data in the signature scripts. And if data in the signature script changes, the transaction ID will also change. Okay, so now let's move over to the solution to this. So what SegWit does is that it moves the data out of the signature script and into a separate data structure that we call the witness here. And this witness is more or less attached to the base transaction. The base transaction is now we call the transaction without the witness is called the base transaction. So when we rip out the data from the signature scripts and put it in the witness, the signature scripts become empty. And now if you hash this transaction, the base transaction, you will get a transaction ID. And if you change anything in the witness, in anything of this witness data, the signatures or the pub keys, or add data or change any data of the witness, it doesn't affect the transaction ID because the witness is not included when you hash the base transaction. So you can change the witness all you want, but that won't change the transaction ID. And that eliminates all known problems with transaction IDs or with the transaction malleability. So suppose that you have a SegWit wallet that knows everything about SegWit, and it has, you have a SegWit enabled wallet, and you want to sell your laptop to Amy. The first thing you need to do is to get a Bitcoin address from your wallet so that you can give your address to Amy. So your wallet will create this address for you. And this is the new address format that came with segregated witness. It starts with BC1, and today it's followed by a Q, and then you have a lot of lowercase letters and numbers. And you give this address to Amy so that she has an address to pay to when she wants to pay for your laptop. Amy inputs this transaction into her wallet. And the wallet will then need to construct a transaction from this with the help of this address. She wants to construct a transaction output with this address. I won't go through all the details of this diagram. I just want to show it because I think it's cool. But I want to highlight a few things here. This address that you see at the top there, the SegWit address, it encodes two pieces of information. First of all, it encodes the witness version. This is a version, and in this case, it's called. In this case, this version is 0, and this version is used for future upgrades of SegWit. And the address also encodes what's called a witness program. And in this example, the witness program is a 20-byte array. This array happens to be a public key hash. It's the same kind of public key hash you're used to from legacy transactions paid to public key hash payments. So it's the same kind of public key hash, nothing new there. So Amy takes these two pieces of information, the witness version and the witness program, and she puts it in the script sig of her output. Sorry, she puts it in the script pub key of her output, or I usually say pub key scripts, sorry. So she puts the version byte and the witness program into the pub key script in her output. So she's paying 0.1 Bitcoin to you for the laptop, and the script sig is a version byte and the witness program. As you might recall from legacy transactions, hang on, I'm going to zoom in here a bit. As you might recall from legacy transactions, a legacy output would look something like this. It's a small script here with a public key hash in it. And in our example here, we don't have a script of the same kind. We just have a few data pushes. So let's say that Amy does this and she publishes this transaction, and eventually it will get confirmed in a block. So now you can give your laptop to Amy, right? So that deal is done. Amy has the laptop, you have the 0.1 Bitcoin. And now you want to spend this coin. You want to buy a popcorn machine for this money. So how would you do that? How would you spend this output to buy a popcorn machine? Well, you create a new transaction that you see over here, this transaction here. So you create a transaction that references Amy's transaction and the output that Amy created for you. but you don't add anything in the signature script. You instead add a signature and a public key to the witness instead. So the signature script is empty and the signature and public key is entered into the witness. So this is the feature that we saw earlier, where you rip out the data from the signature script and put it in the witness to avoid transaction malleability. Okay, so you create this transaction and you add an output to the popcorn guy here of 0.09 Bitcoin. And then you send this transaction out to the Bitcoin network. And then it will reach a node, and a node will probably want to verify this transaction. So let's see how this transaction is verified. The node will look at the output of Amy's transaction. I'm sorry if I look away from the camera because I need to look where I point in the diagram. The node will have a look at the output of this transaction and see the node also is a SegWit enabled node. So this node knows everything about SegWit. And it notices that the output consists of a 0 byte followed by a 20 byte array. And this is a specific pattern that it looks for. So it finds this pattern, and from this pattern, it can conclude that this is a pay to witness public key hash. And if it encounters this pattern, it will trigger certain verification functionality. It will take the pay to witness public key hash template that it has and replace the placeholders with data from the transactions. So this public key hash placeholder will be replaced by the witness program, which is the public key hash. And the signature placeholder and the key placeholder will be replaced by the signature and the public key from the input or from the witness. And then, as you can see here, we have a complete program that resembles very much the program that's run for legacy transactions. In fact, it's the same program, apart from one tiny detail in the object-sig, but I'll not talk about that. So this program is then run and evaluated. If it evaluates to true, this program, the transaction is valid. And in this case, it is true. So this transaction is valid, and the node will gladly forward it to its peers. So a node has now verified the transaction and relayed it to its peers. Great. But eventually, this transaction wants to end up in a block. Some miner wants to include this transaction in a block. So we're going to look at how that's included in a block. Okay, so our transaction in this example is transaction 2. A miner that wants to include transaction 2 in a block, or wants to create a block at all, creates a block just as it did before. It creates a Merkle tree of all the base transactions and calculates the Merkle root that it puts into the block header here. So it creates a Merkle root of all the base transactions. As you recall, the base transaction is the transaction without the witness data. So this is just the base transactions without the witness. And this is exactly how it was done before SegWit 2, apart from one little tiny detail here. And that's this little fella here. This is the so-called witness commitment. So it's a hash that's been put into the Coinbase transaction of this block. It's an op return output of the Coinbase transaction that contains this so-called witness commitment. And this is a commitment to all the witnesses of the transactions in this block. So this is the new thing in the block construction. So let's see how this witness commitment is done then. This witness commitment is created pretty much the same way as the Merkle root is created from the base transactions. It's a Merkle tree made from the witness transactions. That is the transactions including the witnesses. So in this way, we get to commit to the witnesses in the Merkle root in the block header. So it's a nested Merkle tree in a way, if you will. Okay, so this is how the transaction is included in the block. And any node that receives this block will be able to verify it in the same way as it was created by calculating this witness commitment and the Merkle root. But eventually this block will reach a node that's not aware of SegWit. An old node that is not upgraded should be able to verify this block successfully. Otherwise, we would have a blockchain split, which is unfortunate. So old nodes need to understand this block and need to successfully verify it. So let's see how an old node would verify this block. And old nodes don't download witnesses because they don't know what a witness is, so they can't download it from their peers. So they only see this data. This is all they see. They see base transactions, and there is a hash in an output of the Coinbase transaction, but that's perfectly legal according to old rules. So nothing new here, nothing illegal. So everything is nice and dandy, and this Merkle tree this Merkle root will compare nicely, will match the Merkle tree of the block header. So there's no problems in verifying this. It's just that it doesn't verify every aspect of this block. It just verifies the aspects that they are used to verify. Okay, but it also, apart from this, it also needs to verify that transaction 2 is okay, and transaction 2 is valid. It also needs to do that with transaction 3, but let's focus on transaction 2 now, because that's our transaction. This old node needs to verify that this SegWit transaction is valid. Of course, it doesn't know it is a SegWit transaction. It just sees a transaction. So what we see here is what the node sees is a transaction with empty signature script. It doesn't see any witness because it hasn't downloaded the witness. And it sees an output with 2 data items in it, meaningless data, to them meaningless data. So this node will do what it always does. It will run the program, starting with the signature script and then run the pub key script after that. So starting with the signature script, it takes nothing from the signature scripts and put it on the stack. So nothing is put on the stack. And then it will run the stuff in the pub key script, which is first it encounters a 0 byte push, a push of 0 byte. So it pushes 0 byte to the stack. And then it will push this 20 byte array that it doesn't know anything about. It just pushes that data because it's told to do it. So this 20 byte array is put on top of the stack. And then the program is finished. There's nothing more to do in this program. So what's left to do is to find out whether the program evaluated to true or not, or if it evaluates successfully. And Bitcoin regards anything If the top item of the stack is non-zero, Bitcoin will regard the script as successful. So in this case, we have a stack, a program stack that has 0 on the bottom and the 20-byte array on the top. And the 20-byte on the top is non-zero. So this script has evaluated to true, which means that the transaction is valid. Yeah, so this is how an old node would verify this transaction. And I think I will stop there and open up for questions.
Okay, I think everyone's unmuted. So anybody have any questions?
Yeah, so how is the witness connected in a block connected to the transaction? Is the Merkle tree from the witnesses exactly the same is exactly the same build as the transaction Merkle tree? So the bottom right transaction and the bottom right witness is exactly the same, so they can check.
Yeah, I'm not sure I understand, but maybe you were asking.
If a block will be relayed, the node have to check if the transaction number 3 on the upper right is valid, right? So they have to check the witness too. The witness is in the Merkle tree on transaction number 1 in your diagram, right?
Yeah.
How do they combine these?
All right. So when you send a block to a SegWit node, you will send the block header and a list of all transactions and all witnesses.
Yeah.
And this, so the block will receive all transactions and all witnesses in order so that it can create this Merkle tree. No, I'm still not sure I understand the question.
How do transaction number 3 compare to the witness transaction number 3? Because it's only the witness, or is there a transaction ID additionally on the witness? So do you know what I mean?
Not really. Does anyone else understand the question? Because I really don't.
I want to check if the witness fits to transaction number 3.
All
above.
Right. So yeah. So.
But it's on a different place, right?
So you wanna verify that this witness actually belongs to this transaction.
Yeah.
Can you see my mouse pointer?
Yeah. Correct.
All right. You actually, I don't think you can. Well, yeah, you can. You just attach it. You can take the witness and attach it to this one, and verify that transaction as if it was a SegWit transaction. So that's not a problem. But I don't think you have to.
So there's a data field refers to transaction number 3 in a witness.
Yeah. Actually, when I draw the transaction like this, when you have the transaction attached to transaction 3, like this,
yeah,
this is actually, well, it's not completely true, because in a witness transaction, the witness is actually an integral part of the transaction. So it might be a bit misleading to draw it like this. So we have there are two versions of the transaction. One version is the base transaction, and another version is the witness transaction. And the base transaction is one data structure, and the witness transaction is another data structure. So depending on which node you're sending transactions to, you're sending different, you're sending either a witness transaction or a base transaction. So you send base transactions to old nodes, and you send witness transactions to witness capable nodes. So they are actually two different data structures, but they are very similar. The difference are that transaction 3 contains a marker flag at the beginning, or this witness transaction contains a marker flag at the beginning of the transaction. And it also contains the witness.
Okay.
So I think the question was, if you're trying to verify a transaction, how do you know where the witness of that transaction is on the other Merkle tree, on the other data structure?
Yeah, right.
You want to verify the witness for that transaction, but it's in a different data structure. So how do you refer to that witness in where is it on the other Merkle tree?
On this Merkle tree, or this?
Well, this is all the same Merkle tree, is it not?
I mean,
so there's a Merkle tree for transactions, and there's a Merkle tree for witnesses. And at least I understood that they were totally separate.
Yes, sort of. This, can you see my pointer here?
Yeah.
Okay. These are the witness transactions that you hash into witness transaction IDs. Witness transactions are not only the witnesses, it's the transactions including the witnesses.
Ah, okay.
So it's both, it's the transactions including the witnesses down here. So so these hashes here are the hashes of the total witness transaction.
So two transactions will be stored efficiently.
Yeah, well, a witness node will only store this transaction, the witness transaction, but an old node will only store the base transaction.
Okay.
So you don't store two versions of it. You store a SegWit node will store this piece of information, this witness transaction here. And if it wants to send this transaction to a non-SegWit node, it takes out the witness part and just sends it.
See, this is where I think there's been a massive hole in my knowledge this whole time, because I thought there was a completely separate Merkle tree.
Yeah, I thought that too.
But this is one Merkle tree that has transactions, pre-SegWit transactions at the top, and then SegWit transactions at the bottom of the same tree, and the witnesses are with those transactions at the bottom of the tree.
Yeah.
So that's a hole in my knowledge for all this time.
So I'm glad you learned something.
Yeah. And then just on how we're defining witness, is witness and signature interchangeable here? What else? How are we defining witness?
The witness is just a data structure that's part of the witness transaction. Yeah, okay. So you mean on a conceptual level, what is a witness?
Is it interchangeable with a signature or with multiple signatures?
Yeah, anything that attests to the validity of the transaction. Like it could be a signature, it could be a hash and several signatures. So,
and a pre-image to a hash could also be a witness.
Yeah.
Okay.
It could. But let me be clear here. The witness is this whole data structure is called the witness, and there is one witness field for each input of the transaction. So this transaction 3 here, has 2 inputs, and each witness field each row in this witness is called a witness field, and the witness field is associated with the corresponding input of the transaction. So what's called a witness of this transaction is this whole square here. And the witness.
Any other questions?
Yeah.
Oh, sorry, Kalle, continue.
No, go ahead. Did we have any questions on? Oh, where did Michael go? Did we have any questions on YouTube? He mentioned some questions there.
I'd like a question, Kalle.
Yeah, sure.
It's Volker. So are there any actual legacy-only nodes left, or I think basically now everything is SegWit, right? All the nodes in the network.
Yeah, I saw some statistics the other day. I can't really remember. Let me check here. There are probably a few, but they're pretty rare these days. One moment. Oh, sorry, no, I can't see it here. I don't know, but there definitely are old nodes on the network still. Old unupgraded nodes. Maybe they are not that economical, those nodes, because if they were economical, the users of those nodes would probably have upgraded by now. But yeah, there are nodes out there.
Okay.
Old nodes, non-SegWit nodes. I think the SegWit was introduced in 0.13 or so, which came in 2016 maybe.
Okay, thank you. But they don't really play a role, right? So it's
no, not really, because they don't verify all aspects of the block. But they, of course, if their users only use legacy transactions, the node will work perfectly for them to verify the legacy part of the transactions. So for them,
but all the SegWit transactions that they see as anyone can spend.
Yes.
If I got that right. So they would be able, any user that runs a non-SegWit node would be able to spend them inside this small community of nodes that still run pre-SegWit. Is that correct?
Well, yes, it will probably get propagated among those nodes, but you can't put. Yeah. You need to have the transaction confirmed. So if a miner tries to create a block with this transaction in it, anyone can spend transaction. If you spend it as an anyone can spend, and try to and if a miner includes that in a block, that block will be invalid according to an overwhelming majority of the nodes on the network.
Yeah. Okay.
So
I forgot about that.
Yeah.
And also it won't be propagated because you're usually not connected to all legacy nodes.
Right.
So
it's going to be hard to get it propagated.
Yeah. Okay. Thank you.
Okay, any other questions? No? Do you still have another section, Kalle?
No, this would...
Oh, that's it. Oh, okay.
If you don't want to, I can talk a little bit about another problem that SegWit solves, but I haven't prepared it much. I have some figures for it, but if you want to, I can talk about what's called quadratic hashing.
whatever you want. If you want to talk about it, you can talk about it. Otherwise, we'll continue with questions.
Yes, please.
What
The
do you want,
quadratic hashing is very interesting.
Okay.
Okay, go for it. Go for it.
Sure. Hang on a second. So there's another problem that SegWit aims to solve, and that's called quadratic hashing. And that basically means that the bigger the transaction gets, the more inputs the transaction has, the harder it is to verify this transaction, or the longer it will take, not just linearly, but quadratically. I think I have, I'm sorry, I need to zoom out a bit here. Sorry. No, that's the one. Sorry. There we are. So the problem with quadratic hashing is that let's say a transaction with 2 inputs takes 1 millisecond to verify. Then a transaction with 4 inputs would take with 4 inputs would take 4 milliseconds. So you double the amount of inputs, but the time to verify the transaction will quadruple. And if you double again from 4 to 8 inputs, the time to verify this transaction will quadruple again to 16 milliseconds. And if you scale this up to 1024 inputs, it would take nearly about 4 minutes to verify this big transaction. And this is called quadratic scaling. When you double the size of the transaction, you will quadruple the time to verify it. This is a major problem that's being solved by SegWit. And I will show you why this happens, why we have this quadratic hashing problem. And let's see how a typical transaction is verified. Or how, yeah, let's see how it's verified. You wanna verify the right transaction here. So step 1 is that you remove everything from the signature scripts, and and then you want to verify the signature for this input here, for the top input, the first input. And you do that by taking the public key hash, the script pub key, and putting the script pub key in the place for the signature scripts. That's just how it is. That's just how it works. And then you hash this transaction, or sign this transaction with a signature that you later put in this place, that you later put in the signature scripts. So now you have created a signature for the first input. Now you need to do the same. You need to create a signature for the second input. You do the same dance again. You clear out all the signature data from this transaction, and you take the script pub key and put it in a signature script place here. And then you sign this transaction. And signing a transaction means first hash it and then encrypt it with a private key. So that's a signature. You encrypt the hash of the transaction. So first you need to do this and sign that, and then you need to do this and sign that. So this means that if you double the size of if you double the number of inputs, or sorry, when you double the number of inputs, you also double its size, more or less. And if you double the number of inputs, you also need to double the number of signatures you need to create. And if you double the size of the transaction, the time to create each signature will double. So when you double the time to create the signature and you double the number of signatures you need to make, then the time to create the signatures is quadratic. And that also goes for when you later verify this transaction. When you want to verify a transaction, it's the same thing. You need to verify in the same way as when you create the signatures. So to verify the transaction, when you need to perform the same dance, replace the public key hash, replace the signature script with the pub key script, and do that for each input. So that's the cause for this quadratic hashing. When you double the number of inputs, you double its size and you double the number of operations you need to do. And each of these operations will also take double time. And Segwit solves this in a neat way. Instead of the dance we talked about earlier, you will create an intermediate hash once and for all. No matter how big or how many inputs you have, you create one intermediate hash that you will reuse for each input. So you create this intermediate hash here, and then for each input you add just the data that's unique for this particular input. So the first input here, or the first signature you make here, takes data from the first input. And then you sign it and put it into the witness. So in this way, if the transaction size doubles, you only need to hash the whole transaction once, and then you have the same, and then you have to make one constant size signature for each input. And this causes the time to verify such a transaction to drop to 0.5 seconds. Instead of 4 minutes, the time to verify it takes 0.5 seconds. So that's quite a bit of a difference. Yeah, that's what I had to say about that. And that was highly unrehearsed. Sorry about that.
It was still very good. I have a second question relating to that, because basically the question is, how is the timing behavior of hashing relative to signing? Which one tends to be slower? Is signing a very slow process, for instance, or is it?
I think if in this case, if we look at this case here, in this case here, if you have a very big transaction in the legacy system, the hashing would take most of the time, because the transaction is so big. So you need to create a hash of a very big value. So you need to hash a lot of data. So in this case, I think the overwhelming time is hashing. And then the actual signing, when you encrypt the hash with a private key, that's only a 32 byte. That's only a 32 byte string.
It's a multiplication, basically.
Yeah.
Because I was wondering when I got to this part of the book, I was wondering because about the quadratic timing, because if hashing takes so much time, it appears illogical to me that in Bitcoin, in the Bitcoin system, everything is always being hashed all the time. Sometimes double hashed, sometimes 1024 hashes on top of each other, like as if it didn't take any time.
Yeah.
That's why I was interested in learning. Is it really a very, very fast thing to do, or?
Yeah.
Because I don't think it is.
No, I mean, when you're talking about a big transaction like this, yeah, that is really a problem. But most of the time in Bitcoin, what you hash, the pieces of data that you hash is pretty small, and you don't do it in stupid ways like this most of the time.
Okay, so it's highly dependent on the size of the data block.
Absolutely, yes, absolutely.
Okay.
So hashing.
I thought it was a lot of setup to be done, because of, like, the initial pattern that you XOR all this stuff with has to be set up, and then like memory allocation stuff. You need to do that for every hashing, I thought.
Yeah, I think you do too. You do need that too, but that's usually very quick for small pieces of data. So.
Okay.
But I'm not an expert in this field, so don't take my word for it.
We're probably the best expert online right now.
Okay, thank you very much.
I assume. Okay, thank you.
Okay, any other questions? So now you are finished, Kalle, right? We've just put in questions and then we're done. Okay.
No secret talks in my back pocket.
But that was very good, thank you. Any other questions from our audience?
You did say you had questions from YouTube?
Yes, I do.
Yeah.
Let's read them out. So this was a question about from earlier. Pierre asks how you came up with the structure for the book, because it's very easy to get lost because everything is so mingled.
Does it mean that it's easy to get lost in the book, or too easy to get lost in Bitcoin?
Oh, I assume Bitcoin.
Yeah, all right. I hope so too.
Yeah, I mean Bitcoin, because everything is so mingled. It's difficult to cut it into pieces because everything affects another part.
Yeah, I totally agree. And that was a major hurdle in the beginning. I had early drafts of outlines that I never really got pleased with. And I actually had a conversation with my wife in the kitchen about it. And we came up with this way to teach Bitcoin together. I have seen similar approaches previously as well. And that just seemed natural. But it just came to me there at the kitchen table discussing this with my wife. I think it was actually her suggesting it. So, and that was a great idea, and it fits this book perfectly, I think.
Perhaps stop sharing your screen now, Kalle. Just so unless there's any particular slide that's relevant.
Yeah, I'll stop sharing. I'll start sharing it again if needed.
Yeah, sounds good. Okay, so I'll continue with the YouTube questions.
Mm-hmm.
So Johnny says he's interested to hear about forks, the changes introduced, and in particular, why so far they have not done very well, e.g. BCH, which increased the block size.
Why they haven't worked out so well?
That's the question.
Because they are they provide nothing new. I think they provide nothing interesting, and they provide less security than Bitcoin provides. So for average users, I don't think. I mean, why use a less secure asset when there is Bitcoin that's very secure comparatively? I mean, Bitcoin Cash has like 1% of the hash power of Bitcoin, which is like tiny. Any miner can cause huge problems in Bitcoin Cash today. I'm just surprised that it hasn't happened to Bitcoin Cash yet, but it probably will.
What hasn't happened to Bitcoin Cash yet?
Double spend attacks. It has happened to other coins, but not Bitcoin Cash. It's just a matter of time, I think. So yeah, I think that they don't. I think they don't work out as well because they are not as good as Bitcoin, not as secure, and not as widely used. So why use it?
I think it feeds into the discussion we were having at the Socratic last week around like what the actual history was around like the initial fork of BCH and then SegWit 2x and all this kind of stuff. Certainly, I thought at the time, and I still think now, SegWit was a very good change. And the Bitcoin Cash guys didn't implement SegWit.
Yeah.
Which I think was a mistake, number one. Number two, I suppose the majority of the developer community stayed on Bitcoin rather than moving to Bitcoin Cash. I think that's another big factor as well. Yeah. And all of the innovation that we've been seeing since the formation of Bitcoin Cash, the vast majority of it has been on Bitcoin. So, I mean, you're seeing Lightning being built on top of Bitcoin. You're not seeing a Lightning network being built on top of Bitcoin Cash.
Yeah.
So it's just not much happened with Bitcoin Cash other than the block size increase.
They are falling hopelessly behind now, especially when Taproot probably gets deployed on Bitcoin. I mean, we are so far ahead of what Bitcoin Cash has achieved. So it's, yeah. I think it's weird that it actually exists still. It's very, very weird.
I suppose it's very hard to kill. They kind of just do a very, very slow death.
Yeah.
So it'll probably be around for many years more, but I don't have too many hopes for it. Okay, so that was Johnny's question. Got a question from Bitcoin Q&A, which is, can you ask Kalle what he's most excited for in the future of Bitcoin? Wallets, BIPs, hardware wallets, etc.
Yeah, I'm excited about Taproot. I think it will bring huge benefits to privacy and blockchain space. It will, with blockchain space, I mean blockchain real estate. Sorry, that came out wrong. But anyway, it will save a lot of space in the blockchain and provide enormous privacy improvements. And I think that's just amazing work from the guys behind those BIPs. So that's the part I'm most excited about, I think. And I'm also excited about descriptor wallets in Bitcoin that's coming. Me and my wife are working on a project that utilizes descriptors in Bitcoin Core to create a wallet on top of Bitcoin Core that uses 2 or 3 multisig. So we're both pretty excited about that. So yeah, that's it for now. And it's hard to keep your eyes off the Bitcoin shorts right now.
The Bitcoin what, sorry?
It's quite hard to keep your eyes off the Bitcoin shorts right now.
What's the word?
You mean the shorting?
No.
The shorts. Oh, the shorts.
The shorts.
The shorts. Oh, for price.
Price shorts.
Okay, yeah. There's been a lot of price movement recently.
Yeah. But that's fun.
Maybe I know it's not in the book. Maybe just explain what Taproot is.
Yeah. So Taproot is SegWit version 1. Actually, I showed you SegWit version 0 in my talk, and Taproot is a major improvement. It will. I won't go into detail, but what it does is that it provides great. It doesn't. Sorry. I came to a blackout here.
Oh, it's fine. It's not in the book, so it's a bit harsh for me to ask you about it.
I did a couple of drawings on it to explain it.
Oh, yeah.
with the illustration. So I put up those on Twitter a couple of months ago, where I explained it with diagrams, which I'm pretty pleased with. But basically, every transaction that you do, as long as your party cooperates with you, and which is 99% of the cases, each transaction will look like a just single signature spend. So everything will look the same on the blockchain, no matter how complex your scripts are. So you can have a lot of different options to spend a coin, but it doesn't show as. And also, if you don't agree and you need to use one of the exit strategies for this contract, there might be multiple exit strategies for the contract. You only have to reveal the one exit strategy that you actually use, and the other are still hidden from the blockchain. So it's that's the major part of it.
Can I ask a question on that? What is the sorry, I just had a mental blank myself there. Oh yeah, so in terms of the privacy, what would be the impact of Taproot on chain analysis?
Yeah, I think it's pretty much the same there. It's well, chain analysis is, if you look at companies like Chainalysis, they get data from exchanges on which addresses belongs to which users. So in those cases, it doesn't really help that much. But if you use very exotic scripts today, those scripts will be easily identifiable on the blockchain because it's only you using it. So, and with Taproot, that's no longer the case. So you won't. So even if you use exotic scripts, no one will see that. So your anonymity set will just grow enormously.
So yeah, the
Okay,
privacy
cool.
benefits, as Kalle says, are really in those complex scripts. So like Lightning, funding channels,
yes,
like complex multi-sigs with hash locks and time locks and all this sort of stuff. That's where the privacy benefit comes in. If you're just sending to single public keys or single addresses, there's no privacy benefit really. It's the privacy of the complex contract around that spend.
Yeah, but even for single sig ordinary payments, you will also gain because all the complex stuff now looks like the same kind that you use. So your anonymity set grows too, but not as much as for the complex guys.
Yep.
Okay, nice, great.
Any other questions?
I've got a question, maybe slightly change the topic. Well, how private is Lightning now?
Good question. More private than on-chain transactions. I mean, a Lightning transaction is very private, but the channels are not much more private than ordinary Bitcoin transactions. So I guess you can still identify what channel belongs to what person in the same way that you can do with ordinary transactions. But the Lightning transactions themselves are extremely private. How private? Well, I don't know. How long is a string? Yeah,
because you can obviously be on Tor as well, can't you? And with private channels.
Yes, but now I'm not a Lightning expert, so I can't really talk about it that much.
It's a very different setup. So there are certain like privacy attacks, like probing, where you can try and find the balances of Lightning nodes, etc. But the core privacy benefit is that there are a lot of transactions that don't make it on chain. So normally if you make a transaction on chain, that's there for everyone to see. But if you're making a transaction on Lightning, unless you're actually closing the channel out, all those transactions aren't going to chain. So at least on the face of it, the privacy benefits are very promising. But there are always other attacks to try and that people like Chainalysis will be orchestrating.
Cool, thanks.
I think the problem is that all your funds are on the same node. So in Bitcoin transactions, your addresses are mostly separated from each other, but in Lightning you have everything on your node with one IP, and if you don't use Tor, it's easy to see how much funds do you have in total, or to at least assume how much funds you have. In Bitcoin, this is more difficult, I think, on chain.
Yeah, I think you have a good point there. Absolutely.
We're kind of repeating history because like Bitcoin initially had paid to IP address. I was hearing the other day. And so we're still with Lightning, at least if you're not using Tor, we're still in the world where your node's connected to your IP address, unfortunately.
Yeah, I don't think you can see the amount of funds, even if you watch the traffic, even if it's not on Tor. What you see is that a lot of transactions are going out and coming in, but you can't see the amounts. As far as I know, might be tiny amounts or huge.
You can't on the face of it, but there's certain attacks. So like you can probe to see if there's enough capacity to go in a certain route, and therefore you can kind of work out that way whether a node has a certain balance. Or you can set up lots of Lightning nodes and people route through all your Lightning nodes, and then you're seeing the whole route. So let's say like someone like LN Big controls literally every node on the network. They will therefore see all traffic.
Yeah, it makes a lot of sense for them. Yeah, okay. And you can also do attacks like you can analyze the graph. So if you, because it's Tor routed, you could actually, you shouldn't be able to know whether you're at what point you are in the route, right? Whether you're close to the endpoint that's sending it or receiving it. But by analyzing the graph, you could find out that, for instance, if the node that I'm getting the transaction from is in a certain position in the topology, then he must be an endpoint, because only if he is an endpoint would it make any sense for them to send the transaction via my node. I'm not very good at explaining that, but you can make some deductions from the topology, which is an attack vector. But personally, I would take Lightning over on-chain any day.
Yeah. I haven't heard about that kind of attack, so I don't quite understand that, but okay.
Well, it's let's say you're connected to you have the, as a Lightning node, you have the full connectivity graph, right, in memory.
Yeah.
Now, if a peer sends a transaction via your node, then you can and you see where it's going, then you can deduct that your node is only on the path, on the shortest, on the ideal path, if the sending node is, if the node that you receive it from is actually the sending node. And it's, I'm sorry, I'm not up to, not up to
you always seem to be drinking during these calls, Volker.
Yeah, I like them. It's always, it's like, it's 8 o'clock or 9 o'clock at night. I like to drink my wine.
It means your participation slowly goes downhill.
definitely. And I've been translating Knut's second book, and I was at chapter 7 last night, and now I'm at chapter 11 at the end. So I translated like 40 pages in overnight. So so
your brain's fried.
totally exhausted. But I know I understood that topology problem at one point. It was very plausible, and you might want to look it up if you're interested in it.
Thank you.
So on Taproot and Lightning, Kalle,
sorry,
on Lightning and Taproot, which project fills you with more excitement? Doing a second edition of Grokking Bitcoin, which would include Taproot, or doing Grokking Lightning?
Probably Taproot, actually. Yeah.
So
I don't know why really, but I mean, I love both projects, but something draws me to layer one. I like layer one very much. It's just a different, very special set of problems there that you don't have on layer two networks. You know, the scarcity of block space, and it's very, the challenges there are just unique compared to other systems. So it's very interesting. I prefer
Lightning
one.
It'll be interesting to see what Andreas's book on mastering Lightning with Lalu and Rene, how that works out, because things do move so much faster on Lightning.
Absolutely, and I'm looking forward to that, to reading that book. Actually, it's going to be very interesting. I only have an abstract understanding on Lightning Network, unfortunately. So I'm pretty lost there.
That'll be your next project after you've done the second edition, including Taproot, Grokking Lightning afterwards. After that. Okay. Any other questions? I think that's done for YouTube. Any other questions from the chat, from people in the call?
Have you been watching IRC or?
Yeah, I think there's only 2 people in the chat, and one of them's me.
Yeah, I was.
So I'm going to persevere with IRC because I think it's cool, and like the majority of developers are on IRC. But perhaps for this, yeah, it might take a bit of effort to get some people.
Well, I got another question then. But when they're talking about Taproot, often you hear, what is it, Taproot and Schnorr signatures, right? This is a separate thing, though. Is that right? Do you know about this and what that is?
What Schnorr signatures is?
Yeah.
Yeah, it's a new signature scheme, or it's not a new signature scheme. It's an old signature scheme that's been around for ages, but it's been encumbered by patents until 2018 or so. And Volker, maybe you can mute.
Oh, sorry.
Never mind. Sorry. Yeah, so Schnorr signatures has been around for ages, but it's just in recent years that you've been able to use it freely. So and it's a signature scheme that's more appropriate for Bitcoin, because it's what do you say? It's a linear system where the sum of 2 public keys can verify a joint signature. You can make sorry, I'm tired. But
yeah, we'll wrap up. It's a long time to ask you to present and answer questions.
Well,
just so Schnorr and Taproot, you need Schnorr for Taproot. Schnorr allows like key aggregation, so that so Taproot is combining all of that complex, like smart contract stuff in a Merkle tree, and then hiding it within what your Taproot or what your address is going to be. And then you need the properties of Schnorr to be able to build pay to Taproot addresses. So
Okay,
Schnorr is
cool.
a new,
So-
it's a new signature scheme. Well, it's not new, but it's no longer patented, and is a replacement for ECDSA. That
Okay,
was,
so-
was the signature scheme Bitcoin was previously using.
So no other real benefits other than it's sort of needed for Taproot. So that would be the benefit. Taproot is the benefit, really.
It's a little smaller, and also allows for key aggregation, so that if you have like a 2 of 2 multi-sig, you only have to get one key and one signature on chain. When before, if you had a 2 of 2, you'd have 2 keys and 2 signatures going on chain, which would be much larger.
Okay, so good for the scarce block space then.
Absolutely, yeah.
Okay.
So
cool,
again, it seems at least from my high level perspective, it seems like a really well designed proposal. Very similar to Segwit actually, but perhaps less dangerous than Segwit.
Thank you for saving me there, Mike.
No worries. I haven't been speaking for 2 hours, so my brain hasn't been fried. Okay, Pierre has a question. Where can we buy those Grokking Bitcoin shirts?
Oh, this one.
We're admiring your t-shirt.
Actually, this is a super rare, super scarce t-shirt. I have a few, left here.
21 million.
So,
Satoshis.
Okay.
21 million Satoshis.
I have a number of ladies t-shirts left. I think I have no male t-shirt, but I will gladly send one t-shirt to a happy winner that Michael draws. Michael, would you like to make a lottery, and we'll
sure.
Okay, I have one small men's t-shirt here and a few ladies t-shirts. That's all that's left.
Okay, I'll try and find some small men or women to take t-shirts.
Women's sizes are various sizes, so just
okay.
So if you can,
I'll do that after the call, because I'm not entirely sure how I'm going to draw those people.
I'm really
pull
small.
the random number out of your ass.
Okay. Did Volker want to say something, or is he too drunk?
I'm really small.
Oh, Volker's really small. Okay, well, perhaps Volker can have it.
Yeah, sure.
His head barely gets up. Head barely gets up to the screen. Okay, well, I think
can I have a question?
Yeah, go for it. Yeah.
Regarding Taproot, I was wondering why in Taproot we use public keys again and not hashes of public keys or addresses. Has anybody an idea why this is used?
Yeah, I do. Because we use public key hashes in legacy, both in SegWit's version 0 and in legacy transactions. But that's a bit of waste of block space, because you need to add first you need the public key hash in the output of a transaction, and then you need to add the public key in the script sig of the spending transaction. So you need to add a lot of data just to be able to verify the transaction. And if we move away from public key hashes and just use plain public keys in the output instead, we save a lot of block space. So that's it. We make it more straightforward that way, and that's one of the reasons. And I think other reasons might have to do with the Schnorr and Taproot. I mean, technicalities there, but one of the major advantages is that we save block space.
So A says in the chat, why was it added in the first place then?
Yeah, good question.
I can give it a go.
No, sorry?
I can give it a go. I can try and answer that question. So I think it made a lot of, we went from, so as we discussed earlier, we went from paid to IP addresses, then we went to paid to pub key, and then we paid to pub key hash. And a pub key hash is smaller than a pub key, right? So that's saving some space.
Yeah.
And then you had paid to script hash, and then you're hashing the script. And so that saves some space until you spend it. and then we had pay to witness script hash.
Yeah.
But now to get the benefits of the key aggregation, you can't hash those. You can't hash those public keys. So if you're going to be, what's that?
Sorry.
Correct me if I'm wrong, but like to be able to do that key aggregation, they need to be plain public keys. If they're hashed, you can't like add two hashes together, or you can't get the same properties that you can with plain like Schnorr public keys.
Yeah, maybe you're right there. I have one comment there on the one of the first steps when we went from pay to public key to pay to public key hash. The pay to public key was actually huge. It was 64 bytes because we had uncompressed public keys back then. So we went from 64 bytes down to 20 bytes, which was a very valid trade-off back then. But now that we have compressed public keys, it's not that much gain anymore to go from 33 bytes down to 20 bytes. So that gain is not worth it anymore. But it was worth it back then when we went from 64 bytes to 20 bytes. So I think it was pretty more obvious back then that we needed it, but it's not anymore.
And then another follow-up is I heard that the quantum thing is not the right answer. So this is in reference to people thinking that hashing the public key provides some protection against quantum computing. And I think this has been one of the major discussion points on Schnorr and Taproot. And I think like Peter Willer and some of the other Taproot authors have gone over this over and over again with people asking about this. Their argument is that one of the arguments is that if we have a quantum computer that comes out of nowhere, it's going to threaten the Bitcoin network anyway. And also there were questions on how much protection the hashing actually provides in that world where a quantum computer comes out of nowhere.
Yeah,
it's actually in today's Bitcoin Optech letter. There's a link to that.
Okay,
did you get the Bitcoin Optech? It's in there. Peter Wolle explains it again.
Cool. What were you going to say, Kalle?
I forgot.
Okay.
I thought it was the reason because if ECDSA cracks or gets broken, you only need to crack ECDSA to get to the private key. So if you hash it, you have to do two cracks initially, the hash algorithm and the ECDSA. This was why I was wondering.
That's right, and that's the classical argument. But as Peter Wolle says, a lot of coins on the blockchain today, like I think it said like 5 million coins, are not protected by a hash, just by the discrete logarithm problem. I mean, it's just protected by digital signatures and not by hashes. So 5 million coins are already vulnerable, which means that if a quantum computer would suddenly appear, then Bitcoin would be pretty much dead, because 5 million coins lost would probably crush the system totally.
Yeah.
I think that's
so your point, Kalle, that Peter has also said is, there are a lot of funds on the network that have exposed the public key.
Yes.
And so they're not protected by a hash anyway. And then there's various arguments where, well, if the quantum computer can break elliptic curve cryptography, then perhaps it can also break the hashing algorithm.
And also there's a slight window between when you publish the transaction until the transaction gets confirmed. And if you have a quantum computer, when you publish the transaction, you reveal the public key. So during the time from when you publish the transaction until it gets confirmed, you are still vulnerable to this quantum attack, because then you have already revealed the public key. So you have like up to an hour or something like that to crack
Or
Can you
if you reuse the addresses, you have the public key in the blockchain too. You can take a lot of time to quantum compute the key.
If you're can you please elaborate why the public key is seen between confirmation and sending?
Yes.
This is unclear to me.
Yeah, maybe I should start sharing my screen again. Hang on a moment. One moment. There it is.
I think we'll wrap up after this, Kalle. So this will be the last
sure.
question.
Yeah. So let's take this transaction, for example. All right, let's take this transaction here. If you create this transaction, you include the public key in the script sig here, in the signature script. And if you publish this transaction, you will reveal this public key that corresponds to the public key hash. So the only thing that an attacker will need to do from the time of publication is actually find the private key that corresponds to this public key. Because here you have already revealed what's behind the public key hash, what the public key actually was. So if you have a quantum computer here, you can just crack this, find the private key. And
so even if you use addresses, you put the public key in there?
Yes.
Don't you so you don't put the addresses in there, is it right?
Only if you spend from that address. So you can have an address on the chain and funds are sent to that address. And then if funds are sent to the address, but you aren't spending from the address, then you're not revealing the public key. But as soon as you spend funds from that address, you are revealing the public key.
Ah, yeah, okay. So if you spend from something, then the first public key and not this you are sending to.
Yeah, I only reveal the public key of the address that I'm spending from.
Ah, yeah, okay, sorry. Okay, thank you.
I'll stop sharing again.
Okay, does that answer that question on the public key revealing?
Yeah, thank you.
Okay, excellent. Okay, well, unless anyone's got any other questions, I don't think anyone on YouTube has. I don't think anyone on Twitter has. Okay, cool.
Actually,
so we'll wrap
sorry,
up. Okay,
quick one.
go for it. Yeah.
Just in terms of IRC, I'm not on it actually. What do you recommend for a client, IRC client? Or
I'm in the process of transitioning. I'm using Textual at the moment because it was easy to set up. But I need to set up a bouncer personally, because it means when you close the computer, when you go offline, you can't get messages and you don't get the history of the chat. So you need to set up a bouncer so that when you go offline and then come back, you can still see messages people have sent you, or the conversation that's happened while you've been gone away.
Okay.
So it's a little fiddly to get set up. I'm in the process of doing that now, but Textual's a good start, just to, if you're not worried about not receiving messages when you're offline.
What was that? What's it called? Sorry.
Textual on macOS.
Textual.
TEXTUAL.
Okay, cool.
That was the easiest to set up. I'm sure there are much better setups, and yeah, as I said, currently transitioning.
Yeah, I'm also struggling to find a good client. I'm using HexChat and I'm not very pleased with it, but it works.
I think we all need to compare notes and make sure that we've got the best. There were a few tweets in the past about this conversation, or at least some of the core developers saying what setups they were using to connect to IRC. Anyway, enough chat. We shall wrap up. Thank you very much, Kalle. That was amazing. Thank you everyone for attending. Thank you everyone on the YouTube channel watching. We've got a Socratic next week on privacy with Adam Gibson. So details on how to either watch that or perhaps join in. We're working out how many participants we can get on, because we're probably going to be using Jitsi. But yeah, details will be coming shortly on that, but that'll be really interesting next week. But thank you very much, Kalle. I think everyone's unmuted, so we can all applause.
Oh, thanks, Kalle. It was great.
That was great. Thank you, Kalle.
Thank you very much for having me.
No problem.
Pleasure.
It's our pleasure. Thank you very much.
Thank you. Bye.
See you later, guys.
Bye-bye.
Bye.
I promise to finish. See you, mate.
See ya.